Ever wonder why websites crash or orders get mixed up? The culprit is often hidden deep in the way data is stored. Think of a database as a building's blueprint. If it's messy, the whole structure suffers. No matter how skilled the builders, a flawed design leads to problems. That's where normalization comes in, a systematic process for organizing data smartly. Normalization isn't about software or hardware, it's about design. Its main goal? Make databases efficient, reliable, and easy to manage. At its core, normalization breaks down big, complicated tables into smaller, logical ones. The key principle: eliminate data redundancy. Never store the same info in multiple places. This transforms your database from a chaotic collection into a well-organized system. The impact is real. A normalized database is less error-prone, saves space, and is easier to update. Change a piece of info once and it's updated everywhere. No inconsistencies. In the next scenes, we'll break down normalization step by step. You'll see how a little planning prevents massive headaches later. Let's get started. Good database design follows one rule: every piece of data should live in only one place, the single source of truth. When you break this rule, you get data redundancy, storing the same info over and over. Imagine a library spreadsheet. Every time Jane Doe borrows a book, her name and phone number are entered again. If Jane changes her number, the librarian must update every entry, or risk inconsistencies. Redundancy creates a maintenance nightmare and makes your data unreliable. Now, scale this up to millions of customers and orders. Manual updates become impossible. Redundancy also wastes storage and slows down your database. The solution? Store each piece of information only once. This ensures accuracy, saves space, and speeds up your system. Normalization is the process that guides us to this goal. By eliminating redundancy, we build databases that are compact, fast, and trustworthy. Let's see what happens when redundancy is left unchecked. Data redundancy leads to three notorious problems: insertion, update, and deletion anomalies. Insertion anomaly: you can't add new info unless other data is present. For example, you can't add a new library member unless they borrow a book, unless you enter fake data. Update anomaly: change Jane Doe's phone number in one place but miss another, and your data is inconsistent. Deletion anomaly: remove the only book Tom Smith borrowed, and you lose all record of Tom as a member. These aren't just theoretical. They cause real-world headaches, from lost customers to corrupted reports. Poorly structured tables make your data unreliable and hard to maintain. Normalization systematically eliminates these anomalies. By organizing data into logical, related tables, you prevent accidental data loss and inconsistencies. The next step: learning the rules that form the foundation of good database design. Let's start with the basics. First, normal form. Normalization starts with first normal form, or 1NF, the foundation of organized data. Rule 1. Every column must contain only atomic, indivisible values. No lists or multiple items in a single cell. Rule 2. No repeating groups. Don't create columns like product 1, product 2, etc. For example, a project table with employees as Alice and Bob in one cell breaks 1NF. To fix it, each project employee assignment gets its own row. Add a primary key, like project ID plus employee name, to uniquely identify each row. Now, every cell is atomic, and the structure is clear. Here's the result: project ID, project name, employee name. Each row is one assignment. This eliminates confusion and sets the stage for further normalization. But you'll notice some redundancy remains, like repeating project names. That's what the next normal form will address. First normal form is just the beginning. It's about making your data clean and consistent. Next, we'll see how to remove deeper redundancies with second normal form. After 1NF, we move to second normal form, or 2NF. 2NF requires that every non-key attribute depends on the whole primary key, not just part of it. This matters when your table's primary key is made up of multiple columns. In our project table, project name depends only on project ID, not on employee name. This partial dependency causes project names to repeat for every employee. To fix it, split the table: one for projects, project ID, project name, and one for project assignments, project ID, employee name. Now, project name is stored only once, linked by project ID. Update a project's name in one place, and it's reflected everywhere. This structure eliminates redundancy and update anomalies. Achieving 2NF makes your database more efficient and reliable. But there's still one more level of dependency to address: transitive dependencies. Let's see how third normal form takes normalization even further. Third normal form, or 3NF, tackles transitive dependencies, when a non-key attribute depends on another non-key attribute. Example: an employee's table with employee ID, employee name, department, and department location. Department location depends on department, which depends on employee ID, a transitive dependency. This causes department location to repeat for every employee in the same department. If the marketing department moves, you must update every employee's record, risking inconsistencies. To fix this, split the table 1 for employees, employee ID, employee name, department, and 1 for departments, department location. Now, department location is stored only once per department. Employees reference their department and department info is managed separately. This structure eliminates redundancy, update, and deletion anomalies. 3NF ensures every attribute depends only on the primary key, nothing else. Most databases stop here as 3NF provides a solid, reliable structure. But for complex cases, there are even stricter forms. Let's briefly explore BCNF, 4NF, and the idea of denormalization. For most databases, third normal form is enough, but advanced designs sometimes require Boyce Codd normal form, BCNF, or fourth normal form, 4NF. BCNF tightens the rules for tables with overlapping candidate keys, ensuring no hidden dependencies remain. 4NF addresses rare cases with multi-valued dependencies, mainly in complex many-to-many relationships. These forms are used in specialized scenarios. Sometimes, designers intentionally denormalize, adding redundancy back in for performance. Why? Highly normalized databases can be slow to read since queries must join many tables. Denormalization trades some data integrity for faster queries, especially in analytics or reporting systems. For example, sorry convert standard, always denzadan, storing. While we storing product name in order items avoids a join with the products table. Denormalization should be used carefully, only after identifying real performance bottlenecks. Always start with a normalized design, then denormalize if needed. Balance is key. Normalization offers big benefits: less redundancy, more reliable data, and easier maintenance. Each piece of data lives in one place, making updates simple and errors rare. This single source of truth builds trust in your data. Normalized databases are flexible, easy to adapt as business needs change, but there are trade-offs. Highly normalized databases can be complex, with many small tables and relationships. Writing queries often means joining multiple tables, which can slow down data retrieval. For small systems, this isn't a problem, but for massive analytics platforms, performance can suffer. That's why denormalization is sometimes used to speed up reads. The key is to understand your needs and strike the right balance. Normalize for integrity. Denormalize for performance, when necessary. Smart design is always about making informed choices. Database design is the foundation of reliable, scalable systems. Many failures stem from poor data structure, not flashy bugs. Normalization gives us a clear blueprint, step by step from chaos to order. By breaking big tables into focused ones, we eliminate errors and inconsistencies. Third, normal form is usually the sweet spot, efficient, flexible, and trustworthy. The effort spent on good design pays off for years. Mastering normalization is about clarity, precision, and responsibility. Data is valuable. Protecting its integrity is essential. Build on solid principles, and your database becomes a foundation of trust. Data is everywhere. Online shops, social media, even your local library. All these services rely on databases, organized collections of information. Imagine finding a book in a library where everything's in a pile. Chaos. That's why data must be structured logically and efficiently. Well-organized data lets us find, trust, and update information easily. A good database is like a tidy warehouse. Every item in its place, mistakes avoided, and growth possible. Without structure, databases become digital junk drawers, full of errors and inconsistencies. To avoid this, we use a process called database normalization, a step-by-step method to refine data structure and reduce mess. In this video, we'll break down normalization, show why it matters, and how it helps build efficient, dependable databases. So, what is database normalization? It's a systematic way to design tables that minimize data redundancy. Think of it as decluttering, putting each type of data in its own place, just like organizing your wardrobe. Normalization improves data integrity, ensuring accuracy and consistency. If a customer changes their address, you only update it in one place. The main goals: reduce repetition and prevent errors. Storing the same data repeatedly wastes space and invites mistakes. Normalization also prevents data anomalies, problems when inserting, updating, or deleting data. For example, deleting a project shouldn't erase an employee's info. By structuring data properly, normalization makes databases robust and predictable. That's why it's a cornerstone of good database design. Why is normalization so important? In the world of databases, it's a fundamental concept that often gets overlooked, but its impact is huge. Normalization is crucial because it solves data anomalies, insert, update, and delete problems that are caused by redundant or poorly organized data. These anomalies can lead to confusion, errors, and even data loss if not addressed. Take the insertion anomaly, for example. You can't add a new student unless they're enrolled in a course. If Priya hasn't picked a course yet, you're stuck. You can't record her information at all. This means valuable data might never make it into your system. Then there's the update anomaly. If a manager's name changes, you have to update it everywhere it appears in your database. Miss even one spot, and your data becomes inconsistent, leading to confusion and mistakes down the line. The deletion anomaly is just as risky. Deleting a project might accidentally erase all information about an employee who only worked on that project. Suddenly, you lose important records without even realizing it. These issues make databases unreliable, difficult to maintain, and can even disrupt business operations. Over time, small errors can snowball into major problems. Normalization tackles these challenges by ensuring each piece of data has a single, logical home. It organizes information so that every fact is stored only once, reducing confusion and risk. With a properly structured database, you avoid losing, duplicating, or corrupting information. Your data stays accurate, up to date, and easy to manage. That's why normalization is essential for any reliable system. It's the foundation for trustworthy, efficient databases that support your organization's goals. Next, let's see how these problems look in a real-world example so you can recognize them in practice. Understanding anomalies is the first step to building better databases. By learning to spot and fix them, you'll create systems that are robust and dependable. Let's move on to a practical scenario and see normalization in action. Imagine a consulting company trying to keep track of all its employees and projects using just one massive table in a spreadsheet. At first glance, this might seem like a straightforward way to organize information. Everything in one place, easy to access. Each row contains details about an employee and the project they're working on. It sounds simple, right? But as you look closer, problems start to appear. For example, if Aroha is assigned to 2 different projects, her name and information are entered twice. Once for each project. This means the department, project names, and manager names are also repeated in every row where they're relevant. The same data gets copied over and over. As the company grows, more employees join and more projects are added. The table becomes longer and the repetition multiplies. This is classic data redundancy, and it makes the database harder to manage. This setup leads to all sorts of problems called anomalies. For instance, you can't add a new project unless you already have an employee assigned to it. This is known as an insertion anomaly. If a manager's information changes, you have to update it everywhere it appears in the table. Miss a spot, and your data is inconsistent. This is the update anomaly. And if you delete a project, you might accidentally erase all records of an employee's involvement, losing important history. That's the deletion anomaly. The single table approach quickly becomes bloated, confusing, and prone to errors. It's hard to find what you need, and mistakes are easy to make. It's clear that this method isn't sustainable as the company grows. We need a smarter, more organized way to handle our data. That's where normalization comes in. Next, we'll see how this process helps tidy up the mess and makes our database much more efficient. By breaking the data into logical related tables, we can eliminate redundancy, prevent anomalies, and make updates much easier. Let's start with the basics. First normal form, or 1NF. This is the foundation for building a reliable database. Organizing data into clear structured tables is the first step toward a system that's easy to use and maintain. Let's see how normalization works in practice and transform our messy table into something efficient and reliable. Time to tidy up. Normalization starts with first normal form, 1NF. Rule 1. Each cell holds a single value, no lists or group data. Rule 2. Every row must be unique, usually with a primary key. In our example, employee ID alone isn't unique. Aroha appears in multiple rows. Project ID isn't unique either. The solution? Use a composite primary key. Employee ID plus project ID. This ensures each assignment is unique and every cell is atomic. No repeating groups, no multi-valued cells, just clean, organized data. Our table now meets 1NF, but redundancy remains. Next, we'll tackle partial dependencies with second normal form. 1NF is a solid start, but there's more work to do. Let's keep refining. Normalization is a journey. Let's take the next step. On to 2NF. Second normal form, 2NF, builds on 1NF. Every non-key column must depend on the whole primary key. In our table, project name and project manager name depend only on project ID, not employee ID. Employee name and employee dep depend only on employee ID. These are partial dependencies causing redundancy. To fix this, split the table into 3: employees, employee ID, name, dep, projects, project ID, name, manager, and a linking table, employee ID, project ID. Now, each piece of data is stored once and assignments are tracked separately. This structure eliminates partial dependencies and reduces errors. Linking tables connect employees to projects without repeating information. 2NF makes the database cleaner and more efficient. But there's still one more step: removing sneaky dependencies. Let's move to third normal form. Each step brings us closer to a robust database. Ready for 3NF? Let's go! Onward! Third normal form, or 3NF, is a crucial step in database design. It requires that every column in a table depends directly and only on the primary key. There should be no transitive dependencies hiding in your schema. This means that each piece of information is stored in just one place, making your data structure much cleaner and easier to manage. Imagine you decide to add a project manager email column directly to the projects table, thinking it will make things simpler. But now, manager email actually depends on manager name, which itself depends on project ID. This is a classic example of a transitive dependency sneaking in. This setup creates unnecessary redundancy. If a manager oversees several projects, their email address is stored over and over again in the projects table. This not only wastes space, but also increases the risk of inconsistent data if an email changes. To solve this, we create a separate project managers table with columns for manager ID, name, and email, and then link it to the projects table using manager ID as a foreign key. Now, all project details stay in the projects table, while manager information is stored just once in project managers. This separation keeps everything organized and efficient. This approach eliminates update anomalies, reduces errors, and keeps your data tidy and consistent across the database. 3NF ensures that every piece of data has a single logical home, making your database much easier to maintain and scale as your needs grow. With 3NF in place, your database becomes more efficient, reliable, and much easier to maintain over time, even as it grows larger. While there are higher normal forms beyond 3NF, for most practical applications, 3NF is more than sufficient to keep your data organized and robust. Next, we'll briefly touch on those higher normal forms and introduce the concept of denormalization, which sometimes comes into play for performance reasons. The journey doesn't end here. Let's see what's next as we continue exploring the world of database design. Almost there. Beyond 3NF, there are higher forms: VoiceCode, 4NF, 5NF, handling rare, complex cases. For most applications, 3NF is the sweet spot: strong integrity, practical simplicity. Sometimes designers intentionally denormalize, adding redundancy for faster reads. For example, nerds, putting project manager name back in projects to avoid joins. Denormalization is a trade-off: better performance, but more risk of errors. It should be used carefully, only when performance demands it. The key is balancing integrity and speed. Choose the right structure for your needs. Normalization reduces redundancy and creates a single source of truth. Updates are simple: change data in one place and it's reflected everywhere. Normalized databases are flexible and easy to expand. Adding new features is straightforward, just add new tables and links. The main drawback? More tables mean more complex queries and potentially slower reads. Sometimes, denormalization is needed for speed. The best design balances integrity, performance, and simplicity. Mastering normalization means understanding these trade-offs. It's the foundation of reliable, scalable applications. Build smart, and your data will always be in order.